All right, now we're recording. So suppose we have something like x to the 4/3 minus 3x squared plus 5x times 3x to the negative 2/5 plus x to the negative 8 minus 3x to the 7. Don't bother writing this down because we're not going to solve this problem. But suppose we had something like that. How many of you would really enjoy distributing out all of these terms to turn this into one long expression that we could use the power rule for? None of you. That's the answer I was looking for. None of you would really enjoy that, would you? That would suck, right? This sucks. Somebody asks you to take the derivative of this, right? This sucks, especially if all you know is the power rule, because then you have to turn it into a bunch of a long string of plus or minuses, right? This sucks. We don't want to have to do this. We'd like to be able to keep it in the form that it's in and still take its derivative. Conveniently, there's this really great rule that we're going to derive and then use today called the product rule. The product rule is used when you have a multiplication of two different functions, like this is two different functions being multiplied together, to take the derivative. Because unfortunately, you can't just take the derivative of one and take the derivative of the other and multiply them together. It just doesn't work that way. It's very sad. So I've got the product rule written here. This is it. If I have a function u times another function v, the product rule says the derivative of u times v, right, remember one function times the other function, is the first function times the derivative of the second, and then plus the second function times the derivative of the first. That's the rule. You're going to memorize that rule. You're going to use that rule 100 times or more, and you're going to memorize it and know it, and life will be good. But before we use it, we're going to prove it. So if I was looking for the derivative of u times v, I could write it out as a limit of the difference quotient, right? And if my function is u of x times v of x, then we should get u of x plus h times v of x plus h minus u of x times v of x all over h. That's what the difference quotient would look like for the function u times v. Would you guys agree with that? Yeah? Okay, cool. So what we're going to do is, because lots and lots and lots of people before us have done this and know that this works, and I have done this many times and know that it works, and this is arbitrary. You won't have to do this. You won't have to be like expected to know that this is what you should add and subtract in there to be able to simplify this limit. But we're going to add in, a u of x plus h times a v of x into the numerator. And then we're also going to subtract a u of x plus h times a v of x in the numerator. And it should be okay to add in and subtract the same thing, right? That shouldn't be an issue.
Yeah.
Right, because if you add in and subtract it, it's like you put in absolutely nothing at all, right? Right, okay. So plus u of x plus h, v of x, and minus u of x plus h, v of x. Whew, thought I was going to run out of room, but I made it. Okay. Great, that was really fun and exciting. I'm so glad we did that. Why did we do that? Besides that I told you that we
Cancel
had to
stuff
do that.
out.
All right, maybe to cancel some stuff out. Yeah, that seems like that's a reasonable idea. The only thing though that I think we can cancel out is, I could, if I really wanted to, cancel out this u of x plus h v of x and this minus u of x plus h v of x, but there must have been a reason I put those in there. So maybe we can separate this out and write it as two different limits. What do we think?
Yeah.
Yeah, good idea. Yeah, sounds right. Which means we're going to need to sort of group some of this together. Any idea what terms you want to group together and separate out?
Maybe like the U's in one and then the V's in the other.
Okay, so trying to get some U's and V's separated. The only problem is each of them has a U and a V in it, right? So I don't know if I can separate just the U's by themselves and just the V's by themselves. Is there anything that I can factor out of, let's say, all of it?
U.
What?
U.
Well, I can't just factor out U because this whole thing is like one term, right? U of X plus H, U of X, V of X plus H, V of X. Those are terms. The U itself is not really a term. The U of X plus H, though, is a term. So I can't just take a U out of it. So are there any of these terms in blue brackets that I'm putting in here that occur in every single one of them?
X. V of X or U of
Well,
X.
There's not a U of X in each one, right? There's a U of X here, and there's actually I think that's the only U of X. Yeah. But there's a U of X plus H and another U of X plus H and another U of X plus H, but there's no just U of X or just U of X plus H and H. And there's a bunch of V of X's and a V of X plus H, but there's no V of X in every single one, and there's no V of X plus H in every single one. So I don't think there's a single thing in any of these blue brackets that occur in each of the four terms that could be factored. But there are pieces that are the same. Like, for example, this one's got a U of X plus H, and this one's got a U of X plus H, and this one's got a U of X plus H. So maybe we could group together two of those that have a similar thing in them, like that U of X plus H. What do you guys think? How about we group together two of the ones that have a U of X plus H them together? So let's start with the first one. And you guys pick. You want to do the plus one or the minus one?
Plus.
Plus.
Plus. Everybody seems to want to do the plus. Okay, so I'm going to write this with the plus there. And then what's left is a plus, and then a limit as H approaches 0 of the other ones, right? Which is negative U of X V of X minus U of X plus H V of X. And don't worry, that's kind of messy there, but this isn't going to work out, so we're going to erase all that anyway. If I factored out the U of X plus H here, what would that give me? What would be left? A V of X plus H plus a V of X over H? What does that look very similar to?
The derivative of V.
Right, it looks very similar to the derivative of V. True? V of X plus H plus V of X over H, except it would need to be a V of X plus H minus V of X over H, wouldn't it? Because isn't that how the difference quotient works? It's F of X plus H minus F of X. So if this was a minus here, and I factored out the U of X plus H, wouldn't I have the limit as H approaches 0 of V of X plus H minus V of X all over H in there? I think we would. So we've done this just slightly the wrong way. We needed to group together this first term with the one that had a minus in it. So let's try that. I'm going to do this on a new page so we have some more room. I'm going to take this first term and this last term, and I'm going to group them together as their own limit. So we're going to have the limit as H approaches 0 of U of X plus H, V of X plus H, minus, and what are we subtracting there? It's a U of X plus H times a V of X, right? all over
Yep.
h. And then from there, we should be adding a limit as h approaches 0. And what are the two terms that I had left? Should be a positive u of x plus h v of x minus just a u of x v of x. And that should also still be all over h. Everybody good with that or no?
Yep.
Okay. Now I don't expect you guys to have just like seen that on your own. That's why I'm trying to show it to you. But we've got this u of x plus h here and this u of x plus h here that can be factored out. So let's write this as the limit as h approaches 0 of u of x plus h times v of x plus h minus v of x all over h. And what about this other side? What do they have in common?
V of x.
V of x. So we're going to factor out the v of x. And that's going to leave us with u of x plus h minus u of x all over h. So far, good?
Yep.
Okay. With any luck, we should then see that this piece right here, with the limit as h approaches 0 at the front of it, represents what? It's the derivative of
V.
v, right? And this piece right here represents the, with the limit as h
Derivative
approaches
of
0,
u.
the derivative of u. So what we're going to do is we're going to separate this out into a limit as h approaches 0 of u of x plus h times this limit as h approaches 0 of v of x plus h minus v of x over h. And I don't need to put the over h on both of them because I'm separating using multiplication, right? So the h just goes with one of them. I can choose to put it with this one. I could have chosen to put it with this one if I wanted, but that doesn't help me. So I'll put it with this one because it makes this a derivative. We'll do the same thing over here. The limit as h approaches 0 of just v of x times the limit as h approaches 0 of u of x plus h minus u of x all over h. And so what are we left with? As h approaches 0, what's u of x plus h?
U of x.
U of x.
Just u of x. And this whole limit is the derivative of v, dv dx, plus, and this one is the limit as h approaches 0 of v of x. Well, there's no h's in that, so that's just v of x. And this one is the derivative of u with respect to x. And that's the product rule. That's where it comes from. So if I have one function, u, times another function, v, the derivative of that is u times the derivative of v plus v times the derivative of u. Everybody okay with how we derive that?
Yep.
All right. I will not ask you to repeat that derivation ever this whole year. So don't stress about that, but that's how it is done. That's how it's derived. This is what you will memorize, u dv plus v du. And we will apply it to some products of two different functions. And this one's not nearly as bad as this other one that I said sucks. This one doesn't suck as much. But we're going to use the product rule to find the derivative, and then we'll check and make sure what we did is correct, because we can distribute this one out pretty easily and use the power rule to take the derivative. So using the product rule, what should f prime of x be? We can call this function our u function, right? And this function can be our, in a different color. Trying to color code these notes here for all you visual learners out there. So f prime of x should be what? the derivative of a product of two functions is the first function times the derivative of the second function. So what's the derivative of x squared plus 3?
2x.
2x plus the second function. All right, I was going to color code this and then I just didn't do it. But, oh well. X squared plus 3 times the derivative of u, which is
3x squared.
3x squared.
3x squared. So here's u dv v du. Okay. Plus. And if we want to simplify it down, you don't have to always simplify it down, but if we want to, we could. This becomes 2x to the fourth plus 2x plus 3x to the fourth plus 9x squared, or 5x to the fourth plus 9x squared plus 2x. Good or no?
So do you want us to simplify it all the way down if it's easy enough to, like this one was? And if
Yeah,
it's
I mean, if
really
it's
long,
pretty
we just
straight,
leave it?
yeah, if it's pretty straightforward, do this. This is, this is a more convenient notation. If I'm just asking you to find the derivative, this answer up here is totally fine. But you need to be able to do this for pretty much any function, just in case there's a reason that I need you to for the context of the problem. So.
Okay.
All right, so suppose we had distributed this out to begin with. What would we have gotten? X cubed times x squared is x to the fifth, right? And we'd have had a 3x cubed and an x squared and a 3. And if we look at those, what does x to the fifth derivative become? 5x to the fourth, 9x squared, 2x, and the 3 is 0, right? And in this case,
Yep.
distributing it out and then taking the derivative might have been quicker than using the product rule, but there will be plenty of functions all year long where you can't just distribute it out. You're going to have to use the product rule. So, everybody good?
Yep.
All right. Cool. Let's do another one. So it's a product of two functions. Everybody agree that this is a product of two functions?
Yep.
Okay. So if we've got a product of two functions, we're going to use the product rule. We've got u and we've got v. And so we'll do u times the derivative of v. And what's the derivative of v?
2x plus 3.
2x plus 3. Good. Plus our v value, which is x squared plus 3x minus 1, times our derivative of u. What's our derivative of u?
3x squared.
I think I heard some of you, 3x squared. And so that right there is an acceptable answer. If you want to leave it as that. Or if you want to simplify it down, you can. Any questions or issues with that?
Nope.
All right, cool. Let's do another one. So we've got x to the 1/3. I got a question here in the chat. Now the chat's working. That's convenient. All right. Du is just the derivative of x cubed plus 2 with respect to x, so that's the 3x squared. And dv is just the derivative of x squared plus 3x minus 1. That's the 2x plus 3. Now the chat's not working again. Hopefully that helped. All right. So let's take a look at this one. What's our u function going to be? Probably this x
X
to
to
the
the 1/3.
Yep. And our v will be x squared minus 3x plus 2. So
Yep.
if we're going to do the product rule here, f prime of x should be u times the derivative of v plus v times the derivative of u. Right, so our derivative of v, x squared minus 3x plus 2, gives us 2x minus 3. And our derivative of u, which is x to the 1/3, gives us 1/3 x to the negative 2/3. Everybody good with that?
Yeah.
Okay. Now,
Yep.
that answer is perfectly good enough if we're just looking for f prime of x. But if we have to do some other work with it, like finding all values at which it has a horizontal or a vertical tangent line, that becomes a little bit more complicated. So we're going to have to be able to simplify this down in order to do that. And so any ideas on how we're going to simplify this expression out?
Distribute.
Okay, one thing we could do is distribute it out. Now, if we distribute all this out, x to the 1/3 times the 2x, that's 2x to the 4/3, right? Minus 3x to the 1/3, and all this other distributing, we're just going to get a long series of terms. And what do we have to do with like a big long series of terms? It's not quite a polynomial because this has got some fractional exponents, but how would we figure out when it equals 0 for a horizontal tangent line like we talked about the other day?
Do you plug in 0 for x?
We can't plug in 0 for x. We have to figure out when the function itself equals 0, not what the function equals when x is 0, right? So we have to figure out when the derivative, right, for a horizontal tangent line, we want to know when does this equal 0, not what is it when x is 0. Does that make sense?
Yeah.
Yeah. So that's going to be a problem. We're going to have to end up factoring it out to do that. And since we've already got it in a partially factored form, I think it's easier if we just factor it from here. So anybody know what to factor out of this, out of both terms of this?
Could you do x to the 1/3?
All right, x to the 1/3 is a reasonable idea. It's going to complicate things a bit. Let me ask you this question. If I had something like this, what would you factor out of it?
X squared.
X squared, right? What if now I had this? What would you factor out of it?
X.
Just the x, right? You factor out the smallest thing, right? So if I had like this, what would you factor out of it?
X to the negative first. So you would factor out the x to the negative 2/3. Is that what you're saying?
Right. Yep, we want to factor out always the smallest thing we've got. And so the smallest thing we've got is x to the negative 2/3. So we're going to take out that. So if I take out x to the negative 2/3 from x to the 1/3 times 2x minus 3, what does the x to the 1/3 become?
X to the negative 1/3.
Not quite. We took out negative 2/3
Just
from
x.
it. Right. So if we take out negative 2/3 from it, we have to increase this by 2/3 because we took out a negative 2/3. It needs to just become x to the first times 2x minus 3. So remember, if you were to redistribute this back out, x to the negative 2/3 times x to the first, you should add the exponents. Negative 2/3 plus 1 should give you the 1/3. Does that make sense to everybody or no?
Yep.
Okay. And then we've still got over here, we took out the x to the negative 2/3. So we've got a 1/3 times this. So we got 1/3 of x squared minus 1/3 of 3x, which is just x, and then plus 2/3. Good or no?
Good.
Okay. We'll distribute out the x times the 2x minus 3, and then we'll combine our like terms. And what can we do with an x to the negative 2/3? It can drop down to the denominator, right? So we're going to have 2x squared minus 3x plus 1/3 x squared minus x plus 2/3 all over x to the 2/3. And having these like 1/3 in here is probably not super convenient, or the 2/3. So if I can get a common denominator, what can I do with that 3? That's in the denominators. I got these all to have a denominator of 3. What could I do with them?
Move it to the denominator.
Exactly. So let's do that. Common denominator for the 2x squared, if I'm putting a 3 in there, that 2x squared is going to become a 6x squared.
6x squared over 3.
And that minus 3x is going to become a minus 9x. And then we're just going to have a plus x squared. We're going to have a minus 3x, and we're going to have a plus 2 all over 3x to the 2/3. And we should then be able to combine our like terms to give us 7x squared minus 12x, what was it, plus 2 over 3x to the 2/3. All right, 7x squared minus 12x plus 2. Yeah. Okay. Everybody good with that? So then we
Yep.
want to know about horizontal and vertical tangent lines. So the horizontal tangent line, when does this equal 0? How do we figure that out? Yeah, whenever the numerator equals 0. So we'll say 7x squared minus 12x plus 2 equals 0. Does this factor out?
Yeah,
Okay, what does it factor to?
7x minus 2 times x plus 2.
7x minus 2 times x plus 2? I don't think that's going to work.
Oh, 1. No? Sorry, never mind.
I don't think this factors out, does it? Nope.
No, it doesn't.
So this only has horizontal tangent lines when this equals 0, so we can use the quadratic formula real quick to figure that out. At x equals the opposite of b, so 12 plus or minus the square root of 144 minus, what is that, 4 times 7 is 28 times 2 is 56 all over 14. And
Yep.
what is that? That's 88 inside of there, I think. And the square root of 88, if we want to simplify that down, we can take a 4 out of that, right? That's 2 root 22. So 12 plus or minus 2 root 22 over 14, which gives us 6 plus or minus root 22 over 7. Fun, huh?
Totally.
Yeah. And when would it have a vertical tangent line? We haven't talked about vertical tangent lines yet, I don't think. But a vertical tangent line should occur when the slope of the tangent line is
Opposite.
undefined, right? Yeah, when it doesn't exist, right? Because a vertical line has a slope that is undefined. So when will this be undefined?
When the denominator equals 0.
Yeah.
Right, this is undefined if 3x to the 2/3 equals 0. And when does that happen? When x is
0.
0. So we know when it's got a vertical tangent line. We know when it's got horizontal tangent lines. We've answered all the questions. Any issues with that? Any questions on that? Does that make sense?
Wait, why can you set the numerator to get the horizontal tangent line again?
Because it says that for a horizontal tangent line, we're always looking for when that derivative is equal to 0. And if you have a fraction, as long as the numerator is equal to 0, then that's when the whole thing should be equal to 0, right? Does that make sense or not?
Yeah.
Okay. Cool. Are you sure? You sounded a little unsure.
Yeah, I think so. I just have to like do it a couple times to get it, but it makes more sense.
Yeah, so anytime you have a fraction, if the numerator is 0, as long as the denominator is not also 0 at that same value, the whole fraction is 0, right? So, and we'll do that about 50 times this year. Is I'll say when is this derivative equal 0? And it'll be a fraction, and you'll just take the numerator and do the numerator. So. Any other questions on that before we move on?
Can you go back a slide real quick?
Sure.
Okay, thanks.
Can you explain one more time how you got 1/3 x squared minus x plus 2/3? That second.
This part of it right here?
Yeah, that part. Yeah.
Yeah. So we factored out the x to the negative 2/3 from the second piece.
Mm-hmm.
Our second piece of it was right here, right?
Yeah.
So we took out the x to the negative 2/3. So that's gone. So we're just left with the 1/3 times the quadratic here. So I just distributed the 1/3 through 1/3 x squared, a third of negative 3x. Good?
Yeah, thank you.
Yep. Any other questions on that before we get going? Next thing we're going to do is called the quotient rule. So the quotient rule is a way to take the derivative of a function divided by another function. Okay, so if I have u divided by v, if I had x squared plus 1 divided by x squared minus 1, we should be able to use the quotient rule to find that derivative. So I've got the quotient rule written here, but we're going to derive it and prove it first. So the quotient rule is v times the derivative of u minus u times the derivative of v divided by v squared. And, so if we were to use the limit notation for a derivative to find the derivative of u over v, it should become u of x plus h over v of x plus h minus u of x over v of x all over h. Do you guys agree that that's what the limit notation for a function divided by another function should sort of look like at the beginning?
Yeah.
Okay. So the first thing we're going to do with this is we're going to get a common denominator for the stuff in the numerator, and then drop that common denominator into our denominator with the h. So the common denominator should just be v of x times v of x plus h, which will turn this into the limit as h approaches 0 of u of x plus h times v of x minus u of x times v of x plus h all over h times v of x times v of x plus h. Everybody good there?
Yep.
Okay, cool. And so then we've got to figure out something to add in and subtract from the numerator there, just like we did with the other one. And it's not going to be the same thing. This time it's going to be, anybody know offhand?
Nope.
Yeah, I figured as much. That's all right. We're going to add in a u of x times a v of x to the numerator and the denominator. Oh, not to the numerator and the denominator, but we're going to add in a u of x, v of x to the numerator, and we're going to subtract the u of x, v of x from the numerator. So we're going to turn this into the limit as h approaches 0, u of x plus h, v of x, minus u of x, v of x plus h. And then we're going to add plus u of x, v of x, and we're going to subtract u of x, v of x. All over h, v of x plus h. So far good?
Yep.
All right. So same idea as before. We're going to need to group this in some way. So anybody see a good way that they want to group these together? We have a u of x plus h times a v of x. Which one do you want to put with that? Last time we needed to take a positive one and group it with a negative one, right? Because that gives us that subtraction that we need in the difference quotient. So it's either going to get grouped with this one, or it's going to get grouped with the minus u of x, v of x that we added in. What do you guys think?
The minus u of x, v of x.
Yeah, that one's the only one that makes sense because these two don't actually have any terms in common, right? The first two don't have any terms in common to factor out. So if we combine it with the u of x, v of x, the minus u of x, v of x, we'll have a v of x that we can factor out. So let's do that. So we're going to have the limit as h approaches 0 of u, what do we have? U of x plus h, v of x, minus u of x, v of x. And I'm going to just put this only over h for a second here. And then what's going to be left here? We got a u of x, v of x, and a u of x, v of x plus h. Which one of those needs to go first? So that we get the difference quotient, a v of x plus h minus a v of x, or a u of x plus h minus a u of x. I'm going to need to put this one that has the negative in front of it first, right? Because it's the only one that's left that's got an x plus h in it.
Yeah, this one's gonna be hard.
So we're going to do minus the limit as h approaches 0. And effectively, I'm going to factor the negative sign out of these other two terms. So if I take a negative out of negative u of x, v of x plus h, that should become u of x, v of x plus h, minus u of x, v of x. And why is it minus u of x, v of x? Because it was a plus before, right? But I took the negative out of both of these, so that becomes a minus u of x, v of x. Does everybody see that?
Can you explain why you took the negative out again?
Yeah, so the reason I took the negative out is because we need to have the x plus h term come first. We need it to be a positive x plus h, like a positive v of x plus h here, so that when we subtract the v of, the second term, we get the v of x plus h minus v of x over h, which is that difference quotient. So if I don't factor the negative out, this term is a negative term and this term is a positive term, and then it's backwards. I have v of x minus v of x plus h rather than v of x plus h minus v of x.
Okay, that makes sense. Thanks.
Okay, cool. Yep, no problem. And then what have I left out of all of this?
The denominator. I forget what was in there, but
Right, it had a v of x and a v of x plus h, right? So could I do this? Take these two limits and then multiply them. Just I don't quite have room there. Multiply them by the limit as h approaches 0 of 1 over v of x v of x plus h. Would that be okay?
Yeah.
Yeah, because it's the h times the v of x plus h in the denominator. And so if I were to put all of this back together, I would still have an h, right? When these first two limits come back together, we'll just end up with a single h in the denominator. And when I multiply it by the v of x plus h, I'll still have that same denominator. And if I distribute this minus sign through, it comes back to be exactly what I had before. So this should be exactly the same as what we just had on the previous page. So here, this one should be actually quite easy to evaluate. These ones will require us to do a little bit of factoring. So we've got the limit as h approaches 0. What am I going to factor out of this first limit up there?
v of x.
V of x. And in fact, let's make that its own limit, so that we then have next to that the limit as h approaches 0 of u of x plus h minus u of x all over h as the other limit. And then minus, what are we going to factor out of this second one?
U of x.
U of x. And that's going to leave us with the other one as the limit as h approaches 0 of v of x plus h minus v of x all over h. And what's this limit as h approaches 0 of v of x times v of x plus h? As h goes towards 0, what is that?
v of x squared.
That's just v of x times v of x, or v of x squared. And it's in the denominator, so I'll just put it down here underneath all of it, v of x squared. Everybody good with that so far?
Yep.
All right, a little bit complicated maybe, but not too horrible. As h goes towards 0, what's v of x?
v of x.
V of x. And as h goes towards 0, what's u of x plus h minus u of x over h?
The derivative of u of x.
Indeterminate?
Right, it's indeterminate, but it is this limit definition of our derivative. It's the limit as h approaches 0 of u of x plus h minus u of x over h. And that's the derivative of u. So this piece is v, this piece is the derivative of u. What about this piece right here?
u of x.
U of x. And what about this one here?
Derivative of v of x.
Derivative of v of x. So we should finally end up with our final result, which is v times the derivative of u minus u times the derivative of v all over v squared, v of x squared. That's our quotient rule. Any issues or questions on that? Ooh, this has taken us quite a while, hasn't it? We're not getting through nearly as much as I thought we were going to today. Any issues there? Everybody okay with that derivation?
Yep.
All right. Let's do a couple. All right, let's do a couple of them real quick, and then we'll get out of here. I didn't realize we only got 7 minutes left. So let's find the derivative of x squared minus 1 over x squared plus 1. Is this a quotient of two functions?
Yes.
Yes, so you're going to use this quotient rule that you will have memorized. You're going to memorize that quotient rule. So the quotient rule says if I have u over v, the derivative should be v. Oops, I wrote the v. Should be v, which is x squared plus 1, times the derivative of u, which is what?
2x.
2x minus u, which is x squared minus 1, times the derivative of v, which is 2x all over v squared. Good or no?
Yep.
All right, and for these, be nice if we simplify this out a little bit, because these will usually simplify down pretty nicely if it's just a polynomial over a polynomial. So that becomes 2x cubed plus 2x, and then minus 2x cubed, and then minus the minus 1 is plus 1 times the 2x, so plus 2x. And we should get a final answer of 4x over x squared plus 1 squared. Everybody good there?
Yeah.
Cool. Let's do another one. 3x squared minus x plus 2 over 4x squared plus 5. So is it a quotient of two functions?
Yes.
Yes, it is. So you need to use the quotient rule. The quotient rule says take the denominator, v, times the derivative of the numerator, which is
6x minus 1.
6x minus 1 minus the numerator times the derivative of the denominator, which is
8x.
8x all over your denominator squared. Any problems with that? Any issues? If you leave it like this, I have no problem with that. I do not need you to simplify that any further. You might need to. If I asked you, when does this have horizontal tangent lines, you're going to need to simplify your simplify your numerator out. But if I don't ask you that, then you don't need to. Sound good?
Yep.
All right. Let's see. We'll have to. I think we're gonna have to wait on doing this. And now let's do it. We got time. We got 3 minutes. Let's do it. This reciprocal rule is just a. It's just an extension of the quotient rule. So the reciprocal rule says if you have 1 over a function and you're looking for its derivative, then the result is always the opposite of the derivative of that function divided by that function squared. And suppose we have the function 1 over g of x. Suppose 1 over g of x is our u over v for the quotient rule. We should do the v times the derivative of u, and what's the derivative of 1?
0.
0.
0. Minus u times the derivative of v, which is, if we're just looking at g, the derivative of g is g prime of x, all divided by g of x squared. And that simplifies down to the opposite of g prime over g squared, because 0 times g of x goes away. Everybody see that?
Yep.
Okay. So the reciprocal rule is just an extension of the quotient rule. You don't have to memorize it, but it comes up often enough that you might want to, and then it's kind of convenient. So let's do one real quick one using just the reciprocal rule, and then we'll be done for the day. So if we have f of x equals 1 over 2x cubed plus 5x, the reciprocal rule says that the derivative of that should be negative derivative of the denominator, which is what?
6x
6x squared plus 5.
Divided by the denominator squared. And that's definitely a lot easier than writing that out as a difference quotient, I think.
Yeah.